Okay, grade 11s. The other day we looked at doing pH and pOH calculations, and hopefully one of the things that you observed was the relationship between pH and pOH in that they're inverse scale. So if we're looking at pH, a high pH versus a low pH, that this would be acidic and this is basic. And when we're looking at pOH, with the same values, that this is extremely basic and this is extremely acidic. Remembering that 14 is equal to the sum of pH and pOH combined together. Okay, this is a key takeaway point that you need to know. And the reason that we need to know that is because when we're working with acids and bases, we're going to be looking at using different indicators and how they will influence our understanding of the solution that we're working with. So acid-base indicators have a very big role in our labs from here on out. They change color. When something happens in the solution, when it goes from acidic to basic or basic to acidic, there's a color change that happens. So they're very important. They're the base of our understanding of what's going on in our solutions. So acid-base solutions, or indicators, are substances that change color when the acidity changes. Okay? A really common indicator is litmus paper. And so you're quite familiar with this when you did chemistry in grade 9 with Mr. Stewart. And we've also just recently talked about that blue litmus paper turns red when it's acidic, and red litmus paper turns blue when it's basic. Litmus is actually a type of lichen, and they take the paper and they soak it in the solution, and then they let it dry out, and then the reactions are what we're looking at. They're unique because they change color, and they exist in two forms. When we put it in, we might put it in and it's a clear solution, and when we start adding our testing solution, it might change color. And so it depends on the acidity of the solution. So because these phenolphthalein is an indicator. Because these acid-base indicators have really complicated formulas, like phenolphthalein, just the word in and of itself is long and complicated to spell. The chemical composition of it is even longer. So we use abbreviations to help us remember which ones we're using. So litmus is shown by LT, bromothiamyl blue, capital B for bromothiamyl, little b for blue, and an indicator is a capital N, capital I, little n. Okay? The lower pH form is designated as HIN, and that's because here, when we're working on the pH scale, if we put 14 here and 1 here, we know that these particles here, or these solutions here, are acids, and these solutions this way are bases. And acids have to have the hydrogen or the hydronium ion in their empirical formula. So it's indicated by here, HIN. And if it's for the higher pHs, which is basic, we just use the IN negative symbol. Okay? Acid-base indicators. Because each one is made a little bit different, the pH where we see the acid and the base being converted is different forms for each one. And so bromothiamyl blue, when it's in an acid, it's yellow, and when it's in a base, it's blue. So if we were to draw a line down the middle here, anything that's 1.3, so anything from 6 to, say, 6.5 is going to be yellow, and anything, or right in there, 6.3, let's go. And anything here that's 6.6 to 7.6. Actually, let's make this one here 6.5. And let's make this one 6.7 to 7.6 would be blue. And if we had the 6.5 to the 6.7, what color would you anticipate it to be? Well, halfway between these two would be a combination of yellow and blue, which would be green. So you could have a range from yellow to green to blue. And this would be at the 6 end, this would be at the 7.6 end, and this would be somewhere between 6.5 and say 6.7. Okay. Same with phenolphthalein. On the 8.2 end, it would be colorless. And then over here, it would be a bright pink. So this would be 10, and this would be 8.2, and somewhere in the middle is a very faint pink, and that would be 1.8 to 0.9, be around 9.1 approximately. Okay, would be the pH where we would see that very faint pink start to happen. We can find acid-base indicators in our data booklets on the second last page, so page 10, and you can see there's a ton to choose from. Methyl violet, bromocresol green, here's phenolphthalein, and it tells you that the acid version of methyl violet is found at 0 and it's a yellow, and that the base form of methyl violet can be found anywhere above 0.8, and it would be blue. Okay, if we look at bromothiamyl blue, which is one we've talked about, we can see that in acid form it's HBB, and in base form it's BB negative, and it goes from 6 to 7.6, going from yellow to blue. Okay, same thing here with phenolphthalein. It goes, an acid form of phenolphthalein is HPH, which is 8.2, and in indicator in base range, it's pH negative. Now, pay attention, this is capital P little h. When we're talking pH and POH, it's little p capital H. Okay, so don't mix the two up. All right, if you see a capital P little h, we're talking about the indicator. So make sure you're in the habit of writing little p capital H or capital P little h, depending what it is you're talking about. All right. If we were to look really close at the litmus paper, which you guys have used extensively with Mr. Stewart, I know you guys did the red cabbage indicator, and you've used the litmus paper. We have two choices. We have red on this side, and we have blue on this side. Okay, and right around here, you're going to get a little purple region, because red and blue combined together is purple. So if you were to take blue litmus paper and dip it into something that has a pH of, say, 6.5, the blue litmus paper will turn more purple than it will red. And if you were to take red litmus paper and dip it into something that was a 7.5, it would be more purple than it would be blue. So just be aware that right around the midpoint of the pH range is the complementary color of the two colors that are listed. Okay? And you see the mixture of red and blue, which is purple. All right. Acid-base indicators, we have two uses for them. It's to mark the end of a titration, which we're going to do not this unit, but next unit. And it's also used to estimate the pH of a solution. So not only do we have something called litmus paper, which is red to blue or blue to red, we have what's called pH paper. And it runs the range of about 2 to 14. And it changes colors, and there's a little box, and it has a lid, and then it has a color code on each thing. And so it does the 0 to 7 on one side, and then on the flip side it will do 7 to 14. And you just take your strip, which has these little boxes on them. You have to make sure they get wet, and then you see which color they might be, and you compare them up against the strip on the box, and then that's a guesstimate of what your pH is. So here's an example. Solution A, methyl red was red. So if we go to our data booklets and we look up methyl red was red. Okay? And then it says that thymol blue, what that means is that any pH that has to deal with methyl red is going to be 4.8 or lower. So if we were to take a scrap piece of paper, methyl red, it was red. So it's got to be less than or equal to 4.8. Okay? And then we look and we see that thymol blue turned yellow. So we look at our data booklet, and thymol blue, right here, thymol blue turned yellow. So here's yellow for thymol blue. So that means that it's got to be less than 8.0, but it has to be more than 2.8 because 2.8 is yellow as well. So thymol blue was yellow. So it's between 2.8 and 8. And then it said that methyl orange, so methyl orange is the next one. Methyl orange turned red. So when we look here, methyl orange is right here, and it turned red. So it's got to be less than 3.2 because red is anything that's 3.2 and lower. So less than or equal to 3.2. So this 8 is crossed off because it has to be less than 4.8. 3.2 is less than 4.8, so we're going to take that one off the list. And so our pH range is going to be anywhere from 2.8 to 3.2. So we've gotten substantially specific when we're looking at just changes in color. We've gone from 2.8 to 8, and we've narrowed it down to 2.8 to 3.2. Okay, so that's what this tells us. By combining the results, the pH has to be between 2.8 and 3.2. So let's look at some practice questions here. It says that methyl violet was blue. So methyl violet was blue. Methyl orange is yellow. Methyl red was red, and phenolphthalein is colorless. So we go to our data booklet and we start looking for these compounds. Methyl violet was blue. Whoops. Methyl violet was blue, so it has to be at the top end. So it's got to be greater than or equal to 1.6. Methyl orange was yellow, so it has to be 4.4 because you see yellow is at the far end. So 4.4, so it has to be greater than or equal to 4.4. Methyl red, which is right here, was red. So methyl red, when it's red, it's at 4.8. So So it has to be less than or equal to 4.8. And then phenolphthalein was colorless. So when we look way down here at phenolphthalein, colorless is 8.2. So it has to be less than or equal to 8.2. Well, 4.8 is less than 8.2, so we're going to not worry about phenolphthalein. It has to be greater than 4.4, but less than 4.8. 4.4, 1.6 says that it has to be greater than 1.6, which 4.4 is. So that's too low. That's not specific enough. And so it says it has to be greater than 4.4, and it has to be less than or equal to 4.8. So this is our pH range when we use these different indicators to help us figure out what that range is. So this would be methyl violet to methyl blue, or methyl violet turned blue, less than or equal to 1.6. Methyl orange was yellow, greater than 4.4. Methyl red was red, so less than or equal to 4.8. And phenolphthalein was colorless, so less than or equal to 8.0. So the pH of the solution is 4.4 to 4.8 because we have this range here between the two compounds. Okay? Next one says indigo carmine. Indigo carmine was blue. Phenol red was yellow. Bromo cresol green was blue. And methyl red was yellow. So to our pH book we go, to our indicators, and so indigo carmine, way down here, indigo carmine was blue. So we see blue is at the 11.4 end. So it has to be less than or equal to 11.4. So anything below 11.4 and up to 11.4. Phenol red was yellow. So anything less than 6.6 will give us a yellow color. Bromocresol green right here was blue. We see that blue is at the high end, so 5.4. So it has to be greater than or equal to 5.4. And methyl red was yellow, which is at the high end, which is 6.0. So greater than or equal to 6.0. So when we look at this, 5.4 is less than 6, and we're saying it has to be greater than 6. So we're not going to look at the 5.4. When we look at the 11.4, we said it has to be less than 11.4, but this indicator says it has to be less than 6.6. So we're not going to look at that one. And what we're going to see is that we have this range. It has to be greater than 6, and it has to be less than 6.6. So 6.0 to 6.6 is going to be our range. So indigo carmine blue was less than 11.4. Phenol red was less than or equal to 6.6. Bromocresol green was blue, so it has to be greater than or equal to 5.4. Methyl red was yellow, has to be greater than 6.0. And so our range ends up being 6.0 to 6.6. For which you didn't see any of that. There we go. All right. C. Phenolphthalein was colorless, so was colorless. Thymol blue was yellow. Bromocresol green was yellow, and methyl orange was orange. Okay, let's go to our data booklet. Phenolphthalein, way down here. Phenolphthalein was colorless, so it has to be less than 8.2. Okay. Thymol blue, way up at the top, right here. Thymol blue was yellow, so it's going to be from 2.8, which is yellow, to 8, which is also yellow. And bromocresol green was yellow, so it has to be less than or equal to 3.8. And then methyl orange. It says methyl orange is orange, and when we look at methyl orange, the range is 3.2, where we have red, all the way to 4.4, which is yellow. Now, the combination of red and yellow is orange. The way that we figure out the pH is we take the difference between the two pHs. So 4.4 minus 3.2 is going to give us 1.2. And then we want to look at halfway, so then we divide it and we get 0.6. So anything from 3.2 to 3.8 is going to go from red in an ombre type style up to orange, and then from 3.8 it's going to go from orange to yellow. So halfway between 3.2 and 4.4 is 3.8, and that's going to be our orange. So when we look at this, we can say that this is going to be 3.8. So when we go to our chart here, transfer the information, phenolphthalein less than or equal to 8.0, or 8.2, sorry. This is going to be 2.8 to 8.0. Bromocresol is going to be less than or equal to 3.8. Pay attention to this equal part. And then methyl orange was orange. We said that's at 3.8. So it has to be less than 8.2, but it also has to be less than 3.8. So that's going to knock out phenolphthalein, and it's going to knock out this big range that we have here. So it's going to knock out the top end. It has to be less than or equal to 3.8. And when it's orange, we say it's 3.8. So this pH, we can say, is around the range. So that squiggly symbol, I'll write it over here. Squiggly symbol means approximately 3.8. Could be 3.7, could be 3.9. It's in that range. Okay? So this piece here where we take the pH range, so find the first step is to find the range. And then the second step, so high minus low. And then the second step is to divide by 2 to find the halfway point. Because it would take the low end and add that number 2 value. Okay, so here the range from 3.2 to 4.4 is 1.2. That was the first part. The second part was to divide by 2. 1.2 divided by 2 is 0.6. And we're going to take the low end and we're going to add the value from number 2. So 3.2 plus 0.6 is 3.8. Okay, so I'm going to let you guys work on lesson 5, acid-base indicators.